Hi there, Darren here again, and if you made it through, you may have watched the first video. So here is the second. So in the first video, we went through effectively an overview of this tool. This tool is all about exploring data, and that's where we kicked off. We explored the data, we reviewed data for an Auckland climate file. We found that there was an error in there, but they could be multiple. We looked at the actual data itself. Not too interesting to many, but it's there, so you can go ahead and copy that out and bring it into your own process. And finally, we looked at heat maps, looked at varying types of heat maps and how you can manipulate these heat maps to suit your process. Next, we're going to go through just these three here: thermal and comfort. So design day, comfort, and psychrometric. Okay, not exactly in that order, but let's go through them. First of all, design day, fairly simple concept. We've taken the data from the EPW and we presented a bunch of profiles that we think would be meaningful from a data interrogation point of view. Okay, so they're all there for you. You can go ahead and find the hottest day, or indeed find the coldest day in Auckland, which happens to be on August the 11th. So we've post-processed this data for you just so we can extract it. You can do what you need to do with this. You can dump it into an email, into a report, take a screenshot of the whole thing. Completely up to yourself how you want to proceed. Everything else that was in the last video in terms of how you can manipulate the, the gradient here is still applies, so no need to go through that again. Next up, we have, let's go through this in order, comfort. So here we go, comfort. We have a few different things that we can look at. We can look at the idiosyncrasies of natural ventilation. We can look at a stated comfort by hour as a function of different models. And we can look at adaptive band, again, as a function of different models. Again, we will have the manipulation of the chart itself is available down here and shouldn't be too difficult to get your head around. When it comes to the natural ventilation, again, we have a statement here. That statement is only telling us what's available here, but this time it's being controlled as a function of what we apply as the ventilation minimum for the window for natural ventilation. So this is effectively saying, and let's go through it. Let's say we're happy to open a window at 16 degrees. We're happy to keep it open until 30 degrees. No, we're not. We're going to bring that down to, let's say, 25 degrees, where we're starting to cool a home or a building. We're happy to consider the wind conditions as a function of whether that natural ventilation strategy is going to theoretically be in play. And that's for the minimum. Let's actually do this properly. Minimum and then max there. Max is way too high. Let's say that's our scenario there. So under this scenario, a window would be available for ventilation at 16 degrees up until 25 degrees. It can be open between 0 and 6.5. Let's say bring that back down. Let's say 5 meters per second. And let's exclude rainy hours. Now, everything you can see on the screen here that is a 0 means that in our sample file Auckland, natural ventilation is not available. Okay, so it gives a very quick, obvious reason why natural ventilation isn't a strategy for every climate. And it shows that it's highly limited to effectively summerish to shoulder seasons as we go through from January to February to March. One other feature that I will mention, you can do this. Not too sure why you'd want to do it, but you can do it. So there you go. That's natural ventilation. Comfort per hour. Let's have a look at that. Again, we've just got indices here. So these are well-known indices out there, and they effectively change your model in terms of when comfort by hour is being achieved. Okay, so if we go back to the ASHRAE 55, we can see down the bottom, too cold for comfort. This is external comfort, external climate, right? So bear in mind this external climate. Comfortable, too warm. So again, it's showing a real level of limitation in this local climate file as to when comfort is theoretically achieved from an ASHRAE 55 adaptive perspective. Again, the stats will help you articulate exactly what this is all about. Finally, we have the psychrometric. So psychrometric charts are well known to be confusing. We've tried to make this a little bit less confusing for folks, and I guess it has a couple of different applications. So first of all, you can get your favorites up here again and overlay a graphic there in order to tell you, in this case, what the PMV is, or where the comfort range is, and this is a function of the dates that you want, the date and the hours that you want to choose, the metabolic rate, the clothing, and airspeed. Okay, so this all gives you an idea of when the PMV range is going to be available as a function of the climate that you're in, and shows that PMV can be quite limiting. As a way to review this, you can also look at whether you have a high performance envelope in this comfort category, and that's per the 16798 standard, and that will help understand the relative benefits of a higher performance building fabric as opposed to a low performance building fabric. Building fabrics really help comfort. That's why Passive House is very popular these days. So that's a bit about the PMV. There is, of course, ASHRAE 55. Again, you can go ahead and look at that. Similar type of concept. You're just trying to see where you fit in the local climate relative to ASHRAE 55, and you get your stats out there. Now, next up, we have the points here. So points are a way of really identifying specific information on this chart. So if I go ahead and drop in a couple of points, I'm going to just drop one here, left click. That point is starting to give us an idea about what's happening in this at that location. So we have dry bulb, wet bulb, relative humidity, of course. We have the humidity ratio to moisture content, W. We also have the dew point, and finally we have enthalpy, and effectively if we have a change, if we drop in another point, we'll see the change in enthalpy. So let's go ahead and do that. So we have our data points here. Let's go ahead and just drop in another one here. And what we can see is the difference in dry bulb, in wet bulb, in relative humidity. Seems to be on the same line there. In the water content or humidity to moisture content ratio, in the dew point, and then in the enthalpy, in order to give us a reduction in that enthalpy, or the total heat content of the air, combining both sensible and latent heat. So it gives you an idea of how best to size your systems, and it will provide mechanical services engineers an understanding of effectively the total enthalpy removed from point A to point B, and how best to design HVAC systems as a result. So that's one way of doing it. You can keep dropping if you like, and you'll get additional strategies deployed for points 1, points 2, and points 3. You can also just enter a state here if you want to be more specific. So let's go ahead and do that. We're going to go get rid of those there. Let's say dry bulb 20, for example. Relative humidity 65 at a point. There it is there. So we can then see that we have a wet bulb of 15.8. We have a ratio of 9.47. We have a dew point of 13.2. And then we have the enthalpy there sitting at 44.2. So we can be more specific and then push that to 22 as an example, and then we can see the wet bulb temperature jump up, the ratio jump up there, the dew point jump up there, and of course the enthalpy there you go. So that's how to use the psychrometric chart. You again have additional things that you can turn on, turn off, subject to your preference. Okay, so there you go. I'm going to leave that one there, and in the next video I'm going to go on to sun, wind and moisture. Thanks a million for listening. Bye bye.